So for the paper details, the authors are Florian Tramer, Nicholas Carlini, Lyman Brendel, and Alexander Madry. The paper was published in NeurIPS 2020. It has 93 citations, and there's a short version and a long version of the paper. The short version is what everybody read, but we are going to be referencing information that was in the long paper as part of this presentation to give more details. So the outline of this presentation, we're going to start off by talking about the abstract. We're going to go into the introduction. We're going to talk about expectation over transformation, which is a technique we need to cover because it's going to be referenced in the attacks we're going to cover. We're going to talk about 3 of the attacks from the paper. And for each attack, we're going to talk about how the defense works for that we're going to be attacking. And we're going to talk about the paper's attack on said defense. And then finally, we're going to talk about the conclusion and our for and against for the paper. So for the abstract. So the problem that this paper is tackling is that current adversarial defenses that are common in up-to-date papers tend to overestimate the robustness of their models. And the reason they do this is because they're testing their adversarial defenses with automated and general attacks. And these attacks are not the strongest attacks that you could pick for defenses. So they give a false sense of success for these defenses, when in reality, what we're going to see later in the paper is that when you tune an attack specifically for one defense, it has a much higher success rate and is much stronger than general attacks that they were using. So for this paper, it gave 13 adaptive attacks for 13 well-published adversarial defenses that the paper selected to work with. And in addition to explaining the defense and attack, it also provides the methodology for how they created a hypothesis for how to attack a defense and their trials and experimentation, which led to their success of their attacks. So for an introduction, the 3 attacks we're going to be covering are K winners take all, the odds are odd, and mix-up inference. And like I said before, we're going to be talking about EOT, which is used in these attacks, which is why we want to cover it before talking about the actual attacks. And for each of the 3 attacks, we're going to first talk about the defense, and then we're going to explain the attack method on that defense. So first off, expectation over transformation. Expectation over transformation is going to be used in situations where you want to find the gradient of a model that has randomized components or the gradient has been obscured in some way. And as a visual example, you can see, if you take a look at this graph, if the gradient of f of x is randomized or jagged, it's not going to be smooth. Thus, adversarial examples are going to have a hard time being generated on a gradient that's not smooth. So what we want to do is provide an estimation g of x that represents a smooth gradient that can be substituted for this obscured gradient. So some notation to understand about EOT before we talk about the equation is that it makes use of a random classifier, which will produce a random prediction on an input x. And just for notation's sake, based on the paper, FRI represents one instance of the classifier running, providing one prediction. For here, we're going to find the gradient based on that random classifier's prediction for the input x. And we're going to be averaging multiple gradients based on multiple predictions of x. So the full equation, which you saw in the paper, is this, and this is what we were building up to here on the right. And the output of finding multiple gradients based on multiple predictions from our random classifier and averaging them is going to yield a smooth gradient, which will be our gradient to work with and generate adversarial examples off of, which can be thought of as the g of x in our example graph from earlier. So with that knowledge, now we're going to talk about the first defense, K winners take all. And this defense is fairly straightforward. It essentially takes ReLU activation functions, which you would expect to see in a normal model, and it replaces those activation functions with a new activation function known as the KWTA function. And what this function does is it takes all of the, so for all of the activations in a layer, K is specified and it takes the K largest elements or the K largest activations in that layer, and they are allowed to keep their value. And then for every other value that didn't make the cut, it's set to 0. So it has sort of a all or nothing nature. And what this does, what effect it has on the model is that small changes in the input are typically going to have bigger effects later on layers down because you are only taking the K highest and setting everything else to 0. And the paper referred to this as chaotic partitioning. And what this means is that because we have a non-smooth gradient, it's going to be hard to create minimal adversarial examples since minimal adversarial examples rely on a smooth gradient to be effective. So now we're going to talk about the attack on K winners takes all. And the solution here is to just create an estimate of the gradient, smooth version, and to generate adversarial examples off of that. So you can see here on our graph, if f of x is what we're working with and g of x is what we want to find, so that we can have accurate readings and not have these disjoints caused by randomization, we're going to want to estimate local gradients. And we do this by applying multiple normally distributed perturbations to the input to find our estimation. And what I mean by that, and I'm going to explain how we do that specifically, is here's the function that was provided in the paper. And to break this function down, we're going to be estimating average local gradient at the point x with m random perturbations drawn from a standard normal distribution. And what I mean by that is you can see here where the average local gradient or the perturbations are normally distributed, and we take one where it's added and subtracted and compute the cross entropy loss. And through running this about 100 steps, or 100 steps is what was used in the paper with 20,000 random perturbations, we get g of x, which is what we were talking about earlier, which is our smooth gradient representation that we can find minimal adversarial examples on. And this process was shown to be effective enough to bring down the success of the model. And what the key takeaway is from K winners take all is that by introducing the KWT activations function instead of ReLU activation function does is it actually decreases the robustness of the model, is what was found in the paper. And this is because it makes the adversarial training worse than if you were to do nothing.
The next defense we're going to cover is called the odds are odd. And what this defense does is it compares the logics of the classification layer to look for adversarial examples. You can see that if we have a typical convolutional neural network, the logics layer is right here. It's in the very end, and we can use these logics to check for a typical adversarial example. All right, so the entire formula for this defense is going to come up at the end, and we're breaking it down first and going over the pieces. So first, let's start with this formula. you can see it finds the differences between these two functions, the result of these two functions. And this function z computes the logits. So let's say you have an input x, and you put that into z, and it will compute the it will compute the logits for for x at a particular class I, right? And in this case, we are finding the difference between the logits at class I and class y. Now, y is our predicted class from the input, the network's predicted class, and then I is any other class. Now for the next part, we have another part of the formula. And in this part, noise is applied to the input x, and then the logits are computed from that. Now, what you should understand from this is that if an adversarial example, a typical or a normal adversarial example is passed to this and noise is applied, it's different than the result of a normal input image, a clean example. And so, for example, we have our noise delta here. We add it to the input. And then we compare the result of those logits against the logits of x without the noise, and clean examples will be about equal. But adversarial examples, on the other hand, they will not be about equal. They'll be they're likely to be not equal or not similar. And here we have the final part of the equation, and we have this other function, right? And if this function is greater than threshold t, we consider it likely that input x is an adversarial example. Now here is that function right here. It takes what we learned before, and see, it's using this function that we first talked about. And so it's finding the difference in logits for an example input with noise between, it's finding the difference between the logits of an input with noise, and it's finding the difference between an input without noise, and then finds the difference of that. So, you know, it's finding the difference of differences here, and then if it's large enough, if the difference between the input with noise and the original input is large enough, then it's considered an adversarial example. Now here we can take advantage of the properties of that previous equation by expanding it and analyzing it. So if we expand the equation, we get this equation right here, and we can break it down into two parts, S1 and S2. Now, something important to notice here is that, remember, in order for it to consider an adversarial example, these two values have to be large enough to pass the threshold. So our goal here is to keep S1 and S2 down, keep their sum value down as with an adversarial input, and then we succeed in breaking our defense. Now, S1 can be explained simply as large if the model often switches its prediction. So typical or normal adversarial examples, when perturbed, they are often very specific about that perturbation. And if you modify it a bit, then it could easily change its prediction to its true classification. And but we, of course, don't want that to happen. As an adversarial example, we need the S1 to succeed. So we need to make perturbations robust to being changed, to accumulating noise and still retaining that false classification that we want. And S2 is large if the model is overly confident in its prediction. And with adversarial examples, frequently they're curated in such a way to maximize the confidence. And this is taken advantage of here. A normal a normal image that's not adversarial will not typically have those high confidence values. And so S2 takes advantage of that property of adversarial examples, the typical property of adversarial examples, and uses it in its defense. So what we have to, so if you take PGD and EOT and you put them together, and you can reduce S1. S1, remember S1 it gets large when perturbations aren't robust to noise, and EOT helps against that. Now but of course S1 is not enough. We have to modify S2 as well in order to reach below the threshold. So one thing we can note about this attack is that a model's robustness to noise must be similar to or larger than typical input. Normal input will only be able to withstand so much noise before it's misclassified, and so an adversarial example, it must withstand that amount of noise. And secondly, a model's prediction confidence must be similar to typical input. So as we talked about before, typical adversarial images have higher confidences than normal, and we need to reduce that. So the solution to all of this is minimizing this equation right here. If you take the input adversarial input image X and pass it into the logit function Z, then you'll get your logits, and if you pass an adversarial the same adversarial example X, but with a different, not the same adversarial example. If you pass an input X, but with the target with a different class T instead, then you find the difference between the two sets of logits, then you can try to minimize the differences between them and reduce the confidence of the adversarial's prediction, as well as improve robustness to noise, improve its robustness to noise. Oh, and one more thing, if you combine this method with EOT, then it results in even greater performance than before. Secondly, the third defense that we'll cover, the next defense that we'll cover, is mix-up interference. Mix-up interference computes logits with input X and randomly selected clean samples SK. Now, and what this means is that similar in a way to the odds are odd, the mix-up interference takes advantage of the fact that adversarial examples are specific, right? When you perturb them, if you mess up their perturbations, or if you change them, then it's easy for them to classify as the true classification instead of their false, their untrue classification. And mix-up interference includes clean samples of input in addition to your actual input, and so changes your input and it changes the adversarial example a bit and causes it to misclassify. As we can see here, there's also a variable lambda, and lambda represents the proportion of the input that we wish to be clean samples SK instead of input. And here we make the formula the defense makes the assumption that adversarial examples are fine-tuned to a class and do not hold up when slightly modified. And of course, mix-up interference slightly modifies them in order to defend against adversarial examples. Now we attack it. We can very simply attack it by generating adversarial examples such that they are less prone to error upon modification, to misprediction, or rather true prediction upon modification. So we optimize them to be less confident but more generalized perturbations with PGD, and we average the gradient in each step of the attack. that way, this way it's more, it's less, the perturbations are less optimized for a particular set, for a particular part of the uh, this way this way adversarial examples are more optimized towards, are more generalized and less optimized towards a specific part of the distribution. And the gradient must be stable. It must not be unstable, or in other words, constantly mispredict, the adversarial example must always return its misprediction even when slightly modified. And if we combine this attack with EOT, it could also be useful in the future, and improve the attack even further. Now, in the overall, every defense was circumvented with strong adaptive attacks, and attacks. And understanding this, it shows this paper shows that attacks must be simple and designed specifically for the defense. Because if they are not, then it's easy to design a defense that holds up. You have to design attacks for a defense, or else it's not a good, or else it doesn't evaluate well. The attack won't work unless there are no generalized attacks that work on specific defenses. And it's also important to note that for any proposed attack, it is possible to build a non-robust defense that prevents the attack. So if you create some attack that works against a particular defense, then there can be another defense that's created that protects against that, that doesn't fail, that succeeds at preventing that attack. And in all, this paper suggests that future defense research should create stronger adaptive attack evaluations. They should be curated for the defense, and they should not be a bit generalized. Now, for the paper, we have a few points. The paper gives a learning experience, provides a learning experience for the reader. Its intent is to not only prove these, is not only to break these defenses, but teach the reader how to construct their own attacks for their own specific defenses, their own defenses. And in doing so, they hope to improve defense research as a whole, and make attack evaluations more robust and realistic. And this contests modern defense research evaluation methods, because while it's common to have adaptive attacks, meaning they're designed specifically for a defense, it is still oftentimes not enough. They need to be strong adaptive attacks, and not just regular adaptive attacks. And this paper introduces T1 and T6 attack categorization, which can be useful in understanding attacks and how they work, and how they can be applied to different attack approaches can be applied to different defenses. And this paper successfully breaks many modern defenses. Now, against the paper, the definition of strong isn't explicitly defined anywhere. And yet, strong adaptive attacks is the conclusion of this paper, that adaptive attacks must be strong and not weak. I found this to be an issue. And most attacks were done using L infinity, and instead of like L2 or any other types of attacks. And the K winners take solid attack hurts models robustness frequently, and the attack's computational costs are not given, and I think that would be very useful. All right.